Scientists were supposed to be finished with 3 I/ATLAS by now. That was the plan, at least. An interstellar visitor arrives. It lights up the feeds, breaks a few models, splits the community into camps, odd comet on one side, something else on the other. Then it fades, slips back into the dark, and becomes a footnote. On paper, that should have been the end. You hold the press conferences, publish the flagship papers, write the what we learned summaries, move on to the next transient event. That's how astronomy usually works. Except that isn't what happened. Because if you look at what astronomers are actually doing this week, not the headlines, not the social media posts, but the real observing schedules, the telescope allocation requests, the late-night coordination emails, you see something strange. They're still watching it, not casually, not out of nostalgia, but deliberately. Large telescopes that could be pointed anywhere are still tracking a faint speck that is already leaving the inner solar system. Teams that should be reallocating their nights are still carving out time to follow an object that, on paper, should be finished. And that raises the obvious question. Why? Why are scientists still watching 3 I/ATLAS this week? What are they afraid of missing? Because once you understand what they're measuring right now, it becomes clear that the most important part of this object's story may not be what it already did, but what it hasn't done yet. The story that was supposed to end. The expected story is simple. A comet, even a strange one, follows a familiar arc. It enters the inner solar system from the cold, quiet dark. Solar heating ramps up. Ices sublimate. Jets form. Dust lifts off, spreading into a coma and tail. The object brightens as it approaches the sun. That's the photogenic phase. That's what fills wallpapers and time-lapse videos. Then it passes perihelion. After that, everything winds down. Sunlight weakens. Energy drops. Jets shut off. The coma collapses. Brightness fades along a smooth curve that can be described with a single equation. At that point, the science becomes routine. You confirm the decline matches expectations, you archive the data, and eventually the object becomes too faint to justify precious telescope time. The story ends with a graph, not a cliffhanger. That is exactly what should be happening with 3 I/ATLAS right now. But it isn't. The brightness that won't behave. Instead of sliding cleanly down the expected fading curve, 3 I/ATLAS is arguing with the script. When astronomers plot the latest photometric data, brightness across different filters over time, and lay it over the standard fading law for a comet at its distance, the points refuse to behave. There is no dramatic flare, no explosive outburst, no easy headline. What makes this uncomfortable is subtler. Night after night, telescope after telescope, different observatories using different instruments all report the same thing. 3 I/ATLAS is not fading as fast as it should. The deviation is small, persistent, annoyingly consistent. At this stage, the coma should be collapsing into a tired, diffuse glow dominated by old dust coasting away. Instead, the inner region still shows a sharp core. Stacked images reveal tiny bumps in the light curve. Small, but real. And this week matters because the curve is at a decision point. Either it finally bends downward toward the expected decline, or it keeps stalling. If it stalls, it means the current phase of activity is not over. That's the first reason scientists are still watching. They're waiting to see whether 3 I/ATLAS finally chooses to behave like a standard comet, or continues drawing energy from deeper layers longer than any model predicted. That question cannot be answered with a single snapshot. It requires dense sampling, multiple nights, repeated measurements, and that leads directly to the second reason they cannot look away. The spin that won't settle. Early on, researchers noticed something unusual. 3I/ATLAS didn't just shine, it pulsed. Its brightness rose and fell in a pattern that looked less like smooth rotation and more like a heartbeat. Comets vary in brightness all the time. They spin, they tumble, they vent unevenly. That's normal. But the light curve of 3I/ATLAS was different. Instead of a single clean period, one bright side, one dark side, it showed a dominant peak with smaller pulses riding on top. Multiple peaks per rotation. That pattern suggested multiple active regions taking turns. One patch vents strongly, brightness spikes. As it rotates away, a second region swings into sunlight and fires. Then a third. Each peak behaves like a miniature engine. That alone would be interesting. But then the period itself began to drift. When astronomers folded data from multiple nights over a single assumed rotation period, the peaks refused to line up. They kept arriving earlier than expected. The best fit period had to be shortened. Again. And again. That drift told a clear story. The object was spinning up. Jets weren't just venting material, they were applying torque. Like uneven thrusters firing off-center, they were gradually changing the spin state of the nucleus. That's dangerous for a fragile body. For a porous mixture of ice and dust, there is a rotational limit. Exceed it, and centrifugal forces can cause fissures, mass shedding, or outright fragmentation. So scientists are watching closely. Has the spin stabilized, or is it still accelerating? This week's data is critical. If the period holds steady, it suggests the torque has eased. The jets may be calming. Internal stresses may be leveling off. If the period continues to drift, even slightly, it means the forces twisting this object are still active. If fragmentation happens later, people will come back to this week's light curves and ask, did we miss the warning? The dust that refuses to act. Normal, brightness and spin are only part of the story. The other half is written in dust. Normal comet dust behaves predictably. Small grains get pushed away by radiation pressure, forming long tails. Larger grains lag behind, forming trails along the orbit. 3I/ATLAS refused to play by those rules. It developed a striking sunward-pointing structure, an anti-tail. The standard explanation is geometry. Sometimes Earth crosses the orbital plane and dust aligns in a way that looks sunward, but modeling showed that explanation doesn't fully work here. The grains involved appear unusually large, around 10 microns. That size is special, large enough to resist radiation pressure, heavy enough to move sunward, but still light enough to be lifted by gas flow. It's a narrow sweet spot. Even stranger, estimates of the dust cloud's optical depth suggest it is close to 1. That means it's just thick enough to scatter light efficiently and obscure what's behind it, without becoming opaque. Again, that could be coincidence, or it could be architecture. Regardless of interpretation, this dust environment will evolve as the object recedes. Grain streams will stretch, twist, and integrate into the solar system's dust population. This week is the only chance to observe that transition in detail. The orbit that keeps needing help. From a dynamics perspective, 3. A/ATLAS should be simple. An interstellar object enters on a hyperbolic trajectory, gets gently bent by gravity, and leaves. Except that didn't happen cleanly. From early on, orbit solvers had to include non-gravitational acceleration to fit the data. The object was being pushed by its own activity. Not once, continuously. Even now, teams are still measuring its position down to fractions of an arcsecond and feeding that into orbital models. If the required non-gravitational term shrinks, it suggests the activity is fading. If it doesn't, or grows, it means the object is still actively steering itself. That distinction matters. A natural explanation requires a structure capable of sustaining deep internal activity far from the sun. An alternative explanation suggests something else entirely. Either way, the data forces new models. The silence that still matters. Radio observatories have been listening. So far, they've heard nothing. That doesn't close the case. Silence still constrains possibilities. Each hour of listening lowers the upper limit on potential transmissions. And if anything changes, structural failure, final outgassing, unexpected emission, only continued monitoring would catch it. The pattern that won't go away individually, any of these features could be dismissed. Together, they form a pattern. The first interstellar visitor was small, dark, and strangely accelerating without visible gas. The second looked more comet-like but chemically alien. The third combines the worst of both, a small nucleus behaving like a large one, persistent activity, structured dust, self-induced trajectory changes. 3 objects don't define a rule, but they destroy the idea that these visitors are rare and boring. A new field is forming in real time, and this week's data isn't just about 3I/ATLAS. It's about building a playbook, how to respond faster next time, what early anomalies matter, when to escalate observation priority, what normal even means. That's why scientists are still watching. They're not clinging to a fading story. They're training for the next one. Why they're still watching. Because interstellar visitors don't come often. So far, humanity has seen 3. 1 arrived before we were ready. 1 arrived while we were learning. This one arrived when we decided to take it seriously. That's why, this week, people are still on mountaintops and desert arrays aligning guide stars and telling their software, track that dot again. Not because they expect fireworks, but because the quiet deviations matter more. Until 3I/ATLAS finally sinks below the noise floor of our instruments, it still has one job. Tell us what interstellar space is really like. And we still have one job. Listen